This lab is OSPF reference bandwidth. So what I'm going to do in this lab is show you how to change the reference bandwidth for OSPF. The purpose of reference bandwidth is to affect the calculation of OSPF cost on the outgoing interfaces, and it's cumulative. So for example, if the OSPF reference bandwidth default is 100 megabits per second, if you divide that by 1000 megabits per second, you're going to get 1 on all these gigabit links. The calculation can't be lower than 1. So what I needed to do here is just to show you how this works. If this is 100 megabits per second, I've changed this link from gigabit to 100 megabits per second for the bandwidth command. I've also done the same thing here between R2 and R3. This is changed from gigabit to 200 megabits per second. So these are slower links than gigabit, and what I'm going to do is show you how reference bandwidth, if you change the default to 1000, OSPF will be able to differentiate between the gigabit and the lower bandwidth links. And in this case, since 100 megabits is lower, I'm going to have a higher cost through here, and therefore this link R1, R2, R3, R4 will be preferred because it's got a lower cost. The command to change reference bandwidth is autocost reference bandwidth 1000. And what will happen is if I change it to 1000, this link will be 1000 divided by 200, and that'll be 5. So the cost will be 5 between R2 and R3. The cost between R1 and DC1 will be 10. So this link between R1, R2, R3, and R4 will be preferred. So I'm going to go over here and just start with R1 and just show you the configuration. R1's got, all of them have router IDs that are manually configured instead of using the loopbacks. I've got the auto cost reference bandwidth command 1000 there. And it has to be the same for all the routers in the domain. You can't have different reference bandwidth on different routers within the same OSPF routing domain. They all have to be the same. And I've just got passive interface loopback 0 as a standard command. And these 3 commands here, it's all standard on all the routers. I've just got, I don't have any LAN segments. These are all just the WAN connected subnets. And that's just, in this case, there's .1, .2 WAN links going advertising to area 1. And also the loopback here, 192.168.255.1, advertised into area 1. So it's all pretty standard on all the routers. I'm not going to go through all the commands. It's all basically the same. I've just changed the router ID because that has to be unique. And I've added this same command of auto cost reference bandwidth 1000 on all of these routers and advertised, like I said, the WAN connected subnets and the loopback interface. So what I want to do with this is just to start with verifying that the command is working correctly, and just do a show IP OSPF. This is a nice command. It'll give you a lot of information. So just verify the router ID is okay. It's unique. 2.2.2.2. This is for R2. So what I'll do is just go to the bottom here, and reference bandwidth is 1000 megabits per second. So that's correct. That's good. So this is area 1. This is R2 is a member of area 1, so that's correct. It's got 3 interfaces. That would be the 2 WAN connected links as well as the loopback. No authentication, and everything looks fine there. If I go to R1, so R1 the same thing. There's the router ID. Reference bandwidth is 1000. It's area 1, so that's correct. And 3 interfaces. So we'll go to DC1 as well. There's the router ID. And reference bandwidth 1000. And area 1 is correct. I'll go to R3. Router ID is 3333. Matches the number of the router. What I tried to do with the lab. And reference bandwidth is correct, and it's in area 0 area, and this is connected to area 0. That's correct. It's also got an area 1. This is an AVR, so it's got interfaces in 2 different areas, area 0 and area 1. And DC2 should be the same thing. So there's the OSPF ID, router ID, and area 0, and also area 1. And it's got 1000 for the reference bandwidth. And finally R4. There's the router ID, the 4s, and reference bandwidth 1000, and it's error 0. So that's correct as well. So what I want to do now is just take a look at the interface on R1 gig 01. I should see the cost change on there. So there's the cost 10, so that's correct. This is what I want to verify that cost was changed, because that is the purpose of reference bandwidth. Everything else looks fine. And I also want to do the same thing on R2 gig 01. I could check it on DC1 as well, but I'm not going to. I'm just going to outgoing interface of one of them. So there's R2 gig 01. And here I should see a cost of 5. Their cost is 5. So that's basically what I want to see there as well. So that's correct. So it's a cost of 5 since 1000 divided by 200 is 5. It's always the outgoing interface on OSPF. It's the cumulative outgoing interfaces that are all added up to create a cost metric for that route. So in this example here, 1000 divided by 1000 is 1. Then I've got the 1000 divided by 200 is 5. Then I've got a cost of 1 here, since this is gigabit again. So that's 1, 5, and 1 is 7. Then I also have to add 1 for the loopback. Anytime you have a route to a loopback, the loopback itself is going to add a cost of 1. It's just how OSPF does it. So I should see an 8 there for that, and that will be the preferred route instead of this R1, DC1, DC2, R4. Since this would add up to 1000 divided by 100 is 10, then this would be 1000 divided by 2 would just be 1, because that's the lowest you can get. That'd be 10, 11, and then 1 is 12, and then 1 more for the loopback would be 13. So it's going to take R4, R3, R2, R1 in the reverse direction as well. I want to confirm that with the routing table. Just look at OSPF routes. Show IP route OSPF. So I'm going to look at the loop. I'm on R1. I want the loop back for R4. That's the route I'm interested in, 192.168.255.4. So there it is there, and there is the 8 there. So 110 is the administrative distance. 8 is correct, so it's taken that route via 192.168.1.2. It's inter-area route. So because it's advertised from area 0. So if I just go over to this gig 00 here on R2, make sure that's 1.2. Show IP interface brief. So there's gig 00 is 192.168.1.2. There's 00. That's the next hop for R1. We confirm that's actually what it is. In the routing table is 192.168.1.2. So it is taking that path by there it is there, 1.2, by to get to R4. So that's correct. Now if I go to R4, I want to make sure the reverse direction is taking the same path. So I go to IP route OSPF. So same thing. This is the route this time is going to be 192.168.255.1. So fine, there it is, 192.162.55.1. It's got a cost of 8 as well. If it was using the other route, it would be using 13, but it's not. So it's via 192.168.4.1. So that looks good. So 4.1, that should be gig 01 on R3. So we'll go to R3, gig 01. So there's 192.168.4.1. That's gig 01 on R3. Gig 01 R3, there it is. So it's taking the same reverse path back, so that's good. And go back to R4. Verify our work. 4.1, yep, great. 4.1, 4.1. So that verifies then that the reference bandwidth is working correctly, and the lowest cost route is being selected. And again, remember, it's always the cumulative delay or the cumulative cost on the outgoing interface only. So 0, 0, we'd add 0, 0, 0, 1, and 0, 1 here on R3. And in the reverse direction, the outgoing, of course, will be 0, 0, 0, 0, going in the reverse direction. And it just adds them up. And that should basically cover the lab. That is reference bandwidth, and that concludes the lab.